talk about Stephen Herman's Standard Textbook of Electricity, Chapter 16, Alternating Current. And what do we know about alternating current? Let's get rid of this first of all, and then let's go move this down here somewhere. And so we're going to discuss difference between direct and AC, DC and AC. We're going to compute instantaneous values of voltage and current in a sine wave. And we're going to be able to compute peak, RMS, and average values of voltage and current. Discuss the phase relationship or voltage and current in a pure resistive circuit. But keep in mind, there is no such thing as a purely resistive circuit. There's a little inductance or a little capacitance in everything. So there's no pure resistive circuit. Single greatest advantage of AC is that AC can be transformed and DC current cannot. That was the big battle between Edison and Tesla, or GE. And the big battle was Edison wanted to put a generating station on the corner of every block. Think about that, because the wires would have to be gigantic to go very far at all, which would be very cost prohibitive. And we're kind of coming full circle back to that point. A lot of people are getting off the grid, right? They don't want to have power coming from the utility company because they feel it's expensive. Well, it's actually really cheap, but it goes down fairly often, right? No, not fairly often, but it goes down once in a while, right? When we have an earthquake, we have a flood somewhere, you hear about the city power going out for 2 weeks at a time. Okay, a lot of businesses have backup generators. Hospitals all have backup generators, and sometimes they have backup generators and UPS systems, uninterruptible power systems. So they're making their own power, and for that first few minute or two while the generator's starting, everything is carried off a set of batteries on an uninterruptible power system, an UPS system. Okay, you can buy an UP system for your computer at home. It's just got a little battery that takes in AC, converts it to DC, and lets your computer run on the AC that's inverted from the battery. So it's AC, then it becomes DC, and then it becomes AC again, all in one little system, an UP system. And that's the way they all work. Okay. High voltage electrical power can be distributed in smaller wires and lower current. And why is that important? Because the higher the current, the higher the voltage drop, the higher the loss for heating the wires. So if you're going to transmit power from Arizona to California and you have a lot of current, now you want to transfer a lot of power, right? And power is voltage times current, right? P is equal to I times E, right? Well, if you want to transmit, say, 1,000,000 kilowatts, oh, 1,000,000 kilowatts would be a terawatt, right? That'd be a big one. I'm not, a gigawatt. Okay, so a couple of gigawatts we want to transform and send here to California. If you transform that, or you send that here at what we would call operating voltage here, say 480, 277, you're going to lose most of it over that trip. You're going to probably not arrive with any voltage at all. So what they do is they kick the voltage way up to, say, 1,000,000 volts. So now the same amount of power, a gigawatt, let's say, divided by 100,000 volts is a much lower current, right? And we might get here with some voltage left. So we won't lose it. We won't lose a large part of it to the voltage drop, the heat loss of the wire. And that's why transforming power to a higher voltage for transmission is very, very important, because anytime you go a great distance, you need to take it up to a very high voltage and then kick it back down when you get it close to where you want to use it. Okay, and AC allows that, DC does not. Let's go to the next slide. All right. Remember I told you, or maybe I didn't, that everyone calls generating devices by the wrong name. You go to Home Depot and you say, I want one of those generators, but it's not a generator, is it? No, that's an alternator. It's generating power, and that's why everybody calls it a generator, but it's really and truly an alternator because it makes AC. Your car actually is probably making AC under your hood and then transforming it, not transforming it, but it's rectifying it down to DC. Okay, so that's what's going on under your hood. That you have an alternator under there, except everybody really calls it an alternator. And it is. It creates AC power. A generator is something that makes DC power only. So if you see a definition quiz and you see the word generator, you'd better say that that's a device that converts mechanical energy into DC power, not AC. Okay. Okay, graph view of a square wave. Can you even see these blue lines? I don't think we even need to talk about square waves, actually. A square wave alternating current produced by a switch and two batteries. That's not the way you would create any power. But let's talk about making real AC. Now, you know that AC is made by having a magnetic field, a north and a south, next to a coil of wires that are going by. You've seen the windings in an armature. Well, it's kind of the same idea. You have a bunch of windings going past magnetic pole. What happens when a bunch of windings go past the magnetic pole? It induces current into the windings, right? And it induces it in the opposite polarity as the current that induces it. So if you've got this polarity being inducing current into a winding, the polarity for the current in that winding is going to be the opposite. Okay? And as that bunch of wires starts out at 0 degrees, which is flat line on the left, you know what, I'm going to draw on this thing. As we have this point over here, let's say it's our north pole and our south pole. This is probably on our slide someplace, but we're going to talk about it anyway. As we start out at this point, you can see that the windings are halfway in between this pole and this pole. They're not parallel, moving parallel to the poles at all. So you've got a 0 voltage, this point right here. Okay? And as it rotates up and gets to this north point, at that point right there, at this instantaneous point, in that one precise little slice of time, it's very near the North Pole and it's very nearly moving directly across it. So it's going to create the peak voltage. That point right there. And then you can see that as it rotates back down, it's going to come back down to 0. And here's the only disadvantage to AC is that the voltage will fall to 0 2 times per wave, or 1 time per alternation, because this point to this point, this is one alternation. That's a definition term. Okay, so now we're going to look at what happens when it heads back down to the South Pole. It's going to generate power again, only it's going to generate it in the opposite direction. It's not negative, it's just generating current in a different direction. So we have this other peak. This is the same peak numerically, it's just going in a different polarity. And once again, once we come back to this 0 point, it's going to go back to 0. Now this is called a sine wave because from the trigonometric function, in which any point along this line, the sine of that number of degrees times the peak voltage of whatever you may be generating is that 1 point instantaneous voltage. And you need to be able to figure that out. So let's look at, let's say we have just 100 volts at this point right here. So if we have 100 volts there, let's come up to 45 degrees. 45 degrees is right about here, right? Everybody agree with that? What is the sine of 45 degrees? 0.707, that's correct. So we would expect that if this is 100 volts, what voltage would we see right here? 70.7 volts. It's a little on almost 71 volts. Now let's go to 45 degrees back up this way. And how many degrees would that be? If we're going to come over here to the 45 degree point on this side, 45 degrees before 80 would be 80 minus 45, 135 degrees. Thank you very much. 135 degrees. Somebody look up the sine of 135 degrees, please. Pull out your handy dandy TI-30X2S, hit clear once or twice, then put in sine 30, enter. 0.707? Amazing, I tell you. So it's 0.707 over here, right? Okay, now we have just created a zone. And that zone goes from 45 degrees over here to 45 degrees, and the 2 points in between, and everything below that in that block is called RMS power, the equivalent of the DC heating ability. If we had 70.7 DC volts, it would produce the same heat through the same resistor as this 100 volt will create. That's the true RMS power. RMS, root mean square. What does that mean? Average, the average power. Now there's a slight difference between average and between RMS, okay? Because those mathematical terms are slightly different, there are meters that read RMS or average, and they're slightly different. Not a big deal. They're very slightly different, okay? Really. So the point is this, is that you need to know RMS power, because that's what you read when you take a meter and you read AC voltage on a receptacle. So if you're reading 120 volts, and you know that RMS is 0.707 of the peak, let me write this out as a formula now. So we have the peak, let's say we have peak is equal to 0.707 times RMS. I mean, that's backwards, isn't it? Yeah, there we go. I got that backwards. RMS is equal to 707 times peak. Okay, now we know that we're reading the RMS when we read a receptacle. Can I write up here? Nope. So if I'm reading 120 volts as my RMS, what is my peak voltage at that receptacle? I could divide 120 by 0.707, and that will give me 120 divided by 0.707 is equal to the peak, and about 169.7 volts, about that. So the generating companies in the neighborhood are supposed to be generating a peak voltage of 169.7 volts or thereabouts. And you read 120 on everything, because that is the RMS, the heating equivalent, the DC heating equivalent of that power. Okay? So if we read this anywhere along this line, we want to find, let's say that we know the peak. If we know the peak or the RMS, we can find the voltage at any point along that line, right? So let's just take a point and say at 30 degrees, and we know that the peak is 169, let's call it 170 volts. Let's say the peak is 170 volts, and we're going to check the peak, we're going to check the RMS voltage at 30 degrees. What would that be? Sine of 30 times 170 would give us what? Okay, first of all, what's the sine 30 degrees? Say again? 0.5. So half. So it's about 85 volts. Ah, excellent. So it's not linear at all because it's exponential. It goes up very quickly and falls very quickly. Okay, now we can go to the next slide and we can forget about all these drawings. And the rest of these slides are going to probably explain everything I've just said now. Sine waves produced by rotating machines. One sine wave is 360 electrical degrees. In other words, it's going to just explain everything I just said. Voltage at any point along the sine wave is equal to maximum or peak value times the sine of the angle of rotation. We just did an example of that. Here we have another, flux lines cut during second 30 degrees of rotation. Flux lines cut during the last 30 degrees of rotation. Okay. And this is not just a little piece of wire. This is a bundle of windings going around just like our armature does in a motor. Alrighty. And alternating current, instantaneous voltage is the peak times the sine of the angle. We just not only talked about that, but we did an example of it. Okay. If we have a peak of 100 volts, 60 degrees, we'll have 86.6. 30 will have 50 volts. Okay. And same thing. Now, peak to peak. What is peak to peak? In electronics, you will see peak to peak. Generally, we won't use that, but you need to know this definition now and on final day. So peak to peak is the top to the bottom. Very peak top to the very peak bottom. That is peak to peak. Peak to peak is very top to very bottom of a sine wave. RMS values along a sine wave, you know that it's at 45 degrees here at this point. And it's 45 degrees at this point, so we would hit 45 degrees past this point would be here and here. Okay. We know that. In a pure resistive circuit, the voltage and current are in phase. Now we're going to talk about what's happening when you're generating power. Now, it's saying in a pure resistive circuit, in other words, where we're using AC power, where the power is going through some kind of a load, and it's of a pure resistance, then the current and the voltage will happen, the peak voltage and the peak current will happen at the same time. And that is known as being in phase. And it doesn't happen much. Okay? So, skin effect. We don't really need to talk about skin effect. Electrons would much rather go around the outside of the skin of a wire than down the middle. I'm not sure why, but that's just the physical thing that happens in the world. Okay, and then a review of everything we just learned. Okay, and that is over 15 minutes anyway, and I'm trying to keep them shorter. So we're going to stop this one. So there's your chapter. Was that 16? Yep, okay, chapter 16 lecture from Standard Textbook of Electricity.